And we're in a very important subject. Memory, the memory of the computer. We're talking about all the different kinds of memory that your computer has, because actually a computer has a mixture of memory. And I'll give you in other words, I'll give you a example. My father once asked me, if you want to get the most densely packed container, what would you fill it with? Sand or heavy rocks, maybe water, dirt? What would be the densest way? Well, you could say, well, heavy rocks, because they're very dense. Each rock is denser than anything else, but metal rocks, but there'll be gaps between it. So you'll say, sand. Sand I'll fill up my container with sand. It'll be the most dense. Yeah, but even the sand might have some gaps. So water is very heavy. It's not as heavy as sand, but it'll fill every square. So which is the most? Who has? What do you guys think? Give me an answer.
I feel like air. Air would really fill up the entire space.
No, but it would not be dense. I want the most. I want the most electrons and protons and neutrons.
Well, if you're saying that rock is the most dense, I'm assuming the answer you're looking for is fill it up with rock and then fill it up with water to fill the gaps.
Oh, that's the answer I'm looking for. The rock is the most dense. The sand is the next most. So it's not exactly what you said. Even better. First, pour in rocks, then pour in sand. They'll fill in the gaps, but there'll still be some gaps. Now pour water in it. Now you will have the most dense possible filling, because each item has a certain advantage over the other. Water is not quite as dense as sand, but it'll fill in the gaps in between the sands grains, and the sand grains will fill. So a mixture is going to be the most dense. So actually, if you're doing a landfill and you want to build a building on it, you don't just pour in sand. You pour in rocks and sand. Water's not going to help you so much, but you pour in rocks and sand, because that mixture will be the densest. It'll settle the least, and the building won't suffer from settling afterwards as much. So the same thing with memory. Memory on your computer is going to be composed of some memory that's, let's say very fast, but small. Some memory that's bigger and not quite as fast. And some memory that's very big and slow. Because we need all those kinds of things. We need a mixture in order to get a computer to run the best possible way. Okay, but before I get there, here, general history. At the beginning of the computer age, the time to access the memory and the calculation time, in other words, to do an actual computation, were more or less the same. There's something called the calculation cycle time, means how long it takes to process a particular data. That's what we mean by the calculation cycle time. And then there's the access time, is the time it takes to retrieve a particular datum from memory for the purpose of processing. So one thing is to do a load. The second thing is like a load word. The first thing is like an add. Which takes longer, a load word or an add? So we know that a load word takes longer in a MIPS, takes 5 cycles as opposed to an add, which takes 3, maybe 4, but so it takes 4 probably. But they were more or less the same. But due to the rapid technological developments in processors over the year, the calculation time has been much shorter than the memory access time. Well, I mean, right. The truth is, we didn't see that so much in the 5 and the 4. It's almost the same. But forget about that. Just say in general. In general, accessing data is the slowest activity you can do. Processing data is always going to be faster. At the same time, there was also technological developments in memory, but not at the same rate as development of processors. In other words, memory did improve. Accessing memory did improve. The following table shows the rate of technological development. So let's look at this. So here we're coming up with, I actually, this is Moore's Law. You may have heard of Moore's Law, named after Gordon Moore. And it's not so much a law as an observation. It's a mistake to call it, to think of it as a law. Moore's Law is the observation that he made in 1965 that the number of transistors on a dense integrated circuit double every year. In other words, you can squeeze in more transistor, which is computing power, there's more logic gates, twice as many on the same, surface area every year. That's what he noticed in 1965, and it was correct. He said that in 65, and it was true. In 66, it doubled. In 67, 68, for 10 years, it was true. So everyone was like impressed with this prediction, this observation. It was almost, and they said, oh, it's like a law. But then in 1975, he revised his forecast to doubling in every 2 years, not every 1 year, because he saw that the rate was slowing down, he thought. And Moore's prediction, or predictions really, proved accurate for several decades. Recently, the pace has slowed again. But the basic idea of Moore's law is that the amount of logic gates I can squeeze onto a surface area double in every year or every 2 years. So here I say in 3 years in this chart, logic gate doubles in 3 years, gates per square inch or square centimeter, doesn't matter. But the speed also doubles in 3 years. That's the speed of the logic gates. But what about memory? So there's a kind of memory called DRAM, which is a kind of computer memory. The capacity, in other words, this was how many gates on a certain area. This is also kind of how much data, how many bytes I can store in a given space. That also quadruples in 3 years. I mean, double. This was double. This is quadruples in 3 years. That's why you can get like a memory card, that's like tiny, tiny, tiny thing, and it's like holds 16 gigabytes. And it used to be 16 gigabytes was huge. So the size of things is getting smaller. That's the capacity. How much can I get on an inch? But what about the speed? So here we have a problem. It only gets 1.4 times faster in 10 years. That's a big hindrance. There's the DRAM we're getting smaller and smaller, and we're getting more and more memory, but actually we're not much faster than we were 10 years ago.
Could you give an example of what type of memory is DRAM memory?
Well, when you buy a computer and you buy a hard drive of a terabyte, and it tells you it's a terabyte hard drive and 16 gigabytes memory. That's the DRAM.
So that's DRAM?
Mm-hmm. It's either DRAM or SRAM, which we'll talk about in a minute. But it's the RAM, let's say. There's different kinds of RAM. Yeah, go ahead.
Is that a difference between like DDR3 and 4?
We're not going to talk so much about that, about DDR. I might have a slide about DDR. Do I have a slide? Yeah, here, DDRAM. Well, yeah, we'll get to the various. I don't think I talk about it that much because it's not in the material of the course. I wanted to actually. I wanted to talk about it, but I didn't prepare anything about it. Let's talk about. But you're right. DRAM and DDRAM are slightly different. DDRAM is just an improved version of DRAM, but I think I forget what the D stands for actually right now. It might be dense or something like that. I think it's dense. But in any case, that's the DRAM, yes. And then there's the disk. That's the 1 terabyte hard drive that you have. Now, my computer that I'm using, actually, my new laptop, has 2 disks. It has a disk that's an actual moving disk, spinning disk, that's a terabyte. And then it also has a flash disk, which we'll talk about, of only 128 gigabytes. And that's very smart because, like I said with my example of the rocks and the sand and the water, you want to, I have a big one of a spinning disk, and that's slower, but it's large. If I would only have flash memory disk, then my computer would be extremely expensive if I wanted a terabyte of memory of storage space. But the way I have it now, I have like a good compromise. I can put some things that like I don't use very often. I can, like, let's say movies or something, I can put on the large disk, and installations of programs that I use all the time that require speed, I can put on the other disk. None of that is RAM. RAM is volatile memory. volatile memory means that when I turn my computer off, it goes back to 0. So it's good for when I'm running a program, but it's not good for storing my programs. I don't install things. I don't install a program into DRAM. It would get erased when I turn the computer off. I'd lose it. I install it onto the disk. When I run it, it gets transferred from the disk to the DRAM. And as far as speed of disks, they actually double. The capacity also doubles in 3 years, but the speed gets it gets a bit faster, but every 3 years. So they're actually improving faster than the DRAM, which is a big pity because the DRAM is actually very
more important for the speed of the program.
Yeah, it's in a sense it's more important than it holds us. That's going to be the bottleneck, the DRAM. There's SRAM, which is usually faster. Okay, RAM, but we're going to talk about this first. Before we talk about DRAM and SRAM, we're going to talk about RAM in general, which is, I mean, let's say like this: there's no such thing as RAM. It's like saying dog. We talk about dog. There's no such thing as dog. There's poodle, and there's mutt, and there's chihuahua. There's no such thing as dog. You can't get a dog. It is some kind of dog. So same thing with RAM. There's no such thing as RAM. There's kinds of. You can't just buy RAM. You can buy either DRAM or SRAM. But let's talk about RAM in general. So in general, the capacity has gone I mean, this is a very strange chart. He wrote this chart, but I copied it. But it's strange because I don't know what he means by the capacity. I guess he means like average. You buy a computer in 1980, it had 64K. That's true. I had a Commodore 64 in 85, 84. In 84, I bought like a Commodore 64. Why was it called a Commodore 64? It had 64 kilobytes of memory. And the access time to access that memory, of that RAM memory, was 250 nanoseconds. NS is nanoseconds, which means a billionth of a second, 250 billionths of a second. That's how long it took to access the memory. To access a particular byte. Each byte will take me that long, let's say.
What's the cache?
We're going to get to that. We have a whole chapter on cache. We're not going to discuss cache right now. First, we got to discuss memory. Okay, 1986, it was 256 kilobytes. By 1989, it was the normal amount you'd get on a computer would be 4 megabytes. In 1995, the normal amount on a computer was, let's say, 64 megabytes of memory. I mean, now we're up to 16 gigabytes. And the access time has gone down. It used to be 250 nanoseconds, but now it's only 120 nanoseconds. But what you notice from this table is not just that there's improvement in both columns, but that here the improvement is from 64K to 64 mega. In 15 years, it went 1,000 times faster, more capacity. Whereas the access time is only improved by a factor of 2, about twice as fast as it was in 15 years. So you see that the access time is the bottleneck, is what slows us down. Okay. What is RAM? Okay. Memory that can be accessed in a random or non-sequential fashion. We can read or write to any memory cell in any order with the same access time, no matter which address we last accessed. The address to the desired memory is provided by an external device. Fine. So RAM is memory that I can access it in any order I want, and it will not affect the speed at which I access it. So for example, let's say if I'm reading a page, well, let me start with an example that's not exactly accurate. A record player. You're playing a record and you want to jump to a different song. You could just you take your hand and lift up the needle and jump to the exact place on the record and lower the needle and start playing it there. So I can just jump around. I don't have to play them in order. As opposed to a tape, if you remember what a cassette tape was, or if your parents told you about a cassette tape, You could do fast forward and you can get to the end, but you've got to wait. You got to like go through it. If you maybe go faster, but you got to turn. Or a better example, reading from the Torah versus reading from a Chumash. If you want to read from a Chumash, you just flip to the page you want to read. If you want to read from the Torah, you got to start scrolling through. You got to wrap up it's a scroll, so you've got to roll it until you get to the desired location, and then you can start reading. So that we might say that a book is more like RAM in the sense that it's random. RAM stands for random access memory. I can randomly turn from page. I can read page 100, then read page 20, then read page 5. Whereas a scroll, if I want to do that, I have to be turning the scroll a lot. So I have to go forward or backward. I can't just randomly jump around. That's the idea of random versus sequential access. Now, actually, a book is not purely random, because if I'm on page 10, to get to page 11 will take me less time than to get to page 50. I just turn one page, and I know I'm page 11. If I want to get to page 50, I'm going to sort of jump to somewhere I think it is, and then I may have to go back, and then I may have to go forward, and then I'll eventually get to the page that I want. So it's not, the truth is, even though I can jump around, it's not truly random because of what I underline here. It doesn't have the same access time no matter which address we last accessed. In other words, if the access time to page 11 is faster if the page I previously accessed was page 10 than if the page I previously accessed was page 1002. Because if I just accessed 1002, I'm going to have to flip back and try to find page 10, or page 11. But if I just access page 10, I'm going to get right to page 11 in a second. So it's not truly random. What would be random? Let's say if all I had was one page of the book. So to go from one word to another word, my eyes can just jump down the bottom of the page, top of the page. My eyes can sort of scan any part of the page at any time. So that might be closer to real random access. So examples of things that are random access are DDRAM, which I just mentioned here, but I don't really talk about. ROM, flash. We'll go into all these things in detail, except for the DDRAM, I think. The device also provides control lines. For example, when you want to access this memory, you have certain control lines, which are called the CS, which stands for chip select, or chip enable, it could also be called. But what essentially does is it enables that chip, because in order to get 16 gigabytes of memory, it could be that I have 4 sections of 4 gigabytes each. And then each one has an enable. And if I want to access the second one, I'll turn the enable on that 4 gigabytes. So that's the chip select. I select which chip I'm talking about. And then there's output enable or read enable. It's generally called OE, for output enable, but it could be called RE. It's the same thing. Output and reading is the same thing. What I read from the memory, some data. And there's WE, write enable. I guess theoretically called input. I don't know why they don't call it IE, input enable. But anyways, I think it's generally called OE and WE, output and write.
So when you say that the device provides these new memory control lines, so the RAM, like the RAM device, gives these new lines?
No, the whole thing in together. We're going to see in the next slide. Let's go to the next slide. There's a system, a memory system, structure of RAM memory. So you see here, this is called the RAM memory, but there's a whole system here, because there's an address generator. Essentially, he produces the address that I want. The address is M lines, M being like my memory space in bits, how many bits I have. It would be 32. In MIPS, it's 32 bits. And the data lines. Data lines means, am I right? If I'm writing, then then the data is going into memory. If I'm reading, the data is going out of memory into the address generator. So I have two arrowheads. Go either way. Now the CS line or lines is on the top there. That's the chip select. Essentially enabling memory. For some reason, what's missing in the diagram, I copied it from him, but I would have added actually the OE and the WE lines. Maybe that's what he means instead of C. I mean, I could just write here, OE, WE, and CS. All of them. I have to say whether I'm reading or writing. You get the idea. And my point was there could be several of these.
In the CS, the S stands for control what?
No, C stands for chip and S stands for select.
Oh. And that's the control line.
Mm-hmm. That's the control line.
Now, did this have anything to do with the previous control lines we saw, or if this is a completely separate control line?
Well, here's CS. Here it is.
Right, but like in the multi-cycle and like when we saw those diagrams, there we had control lines too.
Well, control lines are control lines. These are different. It's a different control line, but yeah, I mean,
is this connected to that same controller or no?
No. This is the controller. The address generator is the controller.
So RAM has its own controller.
Yes. Yes, exactly. Well said. All right, using RAM. Now we're going to describe what we do. Basically, it's in order to use the RAM, first of all, I have to explain to you a concept called active low, indicated by an overbar. In other words, you put a line over the, let's say you write the word CS and you write a line over it. It's called an overbar. Instead of underline, an overline. And what it means is that a certain line, a certain control line, is active low. What does that mean, active low? Well, we normally think of active meaning if it's a 1, then it's active. And if it's 1 is on, is true, and 0 is false, off. But active low means the opposite. It's active when it's low, when it's 0. In other words, 0 means enable, and 1 means inactive. Why it's like that? Not really important, but just know how to read a diagram. I don't know if I have an example here. Actually, I don't think maybe I have an example. Yeah, see here? See the bar over the CS? That means it's active low. By the way, this is a better diagram. Here you see the memory and you see the address coming in, the data going back and forth. It's the same thing we just saw. And now we have all 3 lines, which is the way it should be. This is the chip select. This is the read. Wait, no, this is the, actually, this is the, why did he call it WR? Yeah, it's a silly name. It should be called the WE. This is the write enable. Oh, he just is WR for write. You know, you got to be flexible when you see diagrams. You got to know what should be there and figure out what it is. WR is for write. It means write enable, or WE. And RD means read, which means read enable. So again, these are all active low, which means if I put a 1 here, it's off. Put a 0 here, it's on. So let's go back. So what do? We want to use this RAM. So these 3 are all active low. So the CS is normally in a high position, which means it's off. That chip is not selected. So to read from the RAM, the address of the byte to be read out is presented on the address lines. The CS is then brought low to then activate it, followed by the OE, the output enable, because we want to enable output. We want it to be able to output to us something because we're doing a read. And that enables the output on the data lines.
So it could be you said this, but does this mean, is this like the active low and like the high, does this come from the fact that like when it's high, it's raised above the circuit, so therefore it doesn't get like electricity or something like that?
You talked too fast and it was mumbled. I couldn't hear you.
I'm just trying to figure out what exactly does it mean when you're saying high or low?
Whether it's 0 or 1.
Oh, okay.
Low is another way of saying 0, and high is another way of saying 1. 1. So it's
Okay,
active
thanks.
low. It's active on 0. Okay, so
So when you say normally high, that means it's normally
off.
but high,
It's
meaning
normally
it's normally off
1.
at 1.
Normally 1, and 1 is inactive. So therefore, it's normally off.
Okay.
After a delay known as the access time, in other words, it takes a certain amount of time for the memory to produce the value that I wanted. The contents of the byte in the memory in the location that I gave it will be available on the input-output lines. In other words, all of a sudden I'll put in this. I'll put in the. Really, I really want to change this to output enable, output enable, and write enable. I don't like to deviate from what he wrote in the Hebrew book, but I can't resist. Probably I'll decide later to put it back, but several lines here. Why is it all screwed up here? The CS, output enable, and write enable. All of those lines are here. So now we're going to explain them, what we do with those lines. And so after delay is known, after a delay known as the access time, the data is on the input-output lines over here. The data I get the data over here. Okay. After reading the data, the CS and the OE are brought high again to turn them off. To write a byte, the address of the byte again is presented on the address lines. The CS is once again brought low. The data to be written is put on the IO lines, and WE is brought low, which enables it, write enable, for the whole access time, for whatever time it takes, whatever is like a clock cycle essentially. Whatever is the access time, it's brought low for that time. WE is then brought high again, and on the rising edge of the WE, the data is written into memory. So in other words, it's like only we lower, we lower the write enable, and we hold it there for a little bit, and then we pull it back and close it off again. And as it closes off, then the data gets written into memory. It's like that's called we never talked about this before, but now we're talking about it. The rising edge of a certain cycle. In other words, we talked about cycles, but actually within the cycle, we can break them up into sub-cycles, into sections of the cycle. And the rising edge, as we end the cycle, we change the value, we change the value on WE, we bring it back to 1, and then the data gets written. Okay, that was how RAM works. Now let's talk about sequential access of memory. Because that was not sequential, that was random access. Sequential access is again, like if somebody doesn't know what a tape cassette is, then I can explain it now, but you can ask. I'm going to assume that you all know what a tape cassette is. It's a magnetic, it's a film of plastic with clay and magnetic particles on it, metallic particles, which can be read by a sensitive magnetic reader. You can tell where the metal particles are, and there know whether it's ones or zeros. In other words, you can have a digital tape. of a tape which stores data digitally. So now before we're mostly going to discuss that random access, but for contrast, we'll discuss now the sequential access. And if you look at this picture, if I'm on A and I want to access B so I can get there right away, I just scroll to the next place and I'm right there. In fact, when I finished reading A, I actually was standing right here, and then I'll just read B. But if I was at B and I want to read A, then it could be that I have a certain kind of tape drive that only goes forward. So it could be that the tape drive, if I want B and I want to read A, it's going to have to go all the way to the end. Then it's going to press a special rewind button. It's going to go all the way back to the beginning, and then start going forward, fast forward till it gets to A. So we see that getting to A will be a lot slower if I'm on B than it would have than getting to A than getting to C, for example. If there's a box here C, then getting to C would be very fast because it's just the next byte. So this is sequential because the speed at which the time required to access some memory is different from some locations, is different from other locations. Certain ones are closer and certain ones are further apart. So a spinning tape drive, a tape drive for sure is sequential. And I propose that even a disk drive is sequential. Why is a disk drive sequential? Because disk drive also has like a head. It's got like plates, circular, flat discs, and the head moves right and left across it like a needle on a record player, and you can lift it up and move it inward or outward. And if you want to read the next data on the same groove, essentially, it's not really a groove, but on the same lane. It's like a lane in a fast highway. But if you want to read the next piece of data on that lane, you don't have to move the head at all. But if you want to go to an inner lane closer to the focus of the circle, then you'll have to move the head inward, and that's a physical operation, a movement of a piece of metal. It takes time, much more than just spinning. And even the disk, if I want to read the next byte on the same lane, it's much faster than if I want to read 10 bytes ahead on the same lane. So, because I have to move the disk over ahead 10 spaces. So a hard disk is sequential, and therefore it's slower. It's slower.
How does it keep track of where the words start and end?
What?
Or how does it keep track of where bytes like start and end?
That's an interesting question. Well, there's a controller. There's a disk controller, and when it reads, it reads byte. It reads bit, reads in 8-bit units, and then the controller tells it how many units to read, and if it's 1 unit, then it goes forward that many bits. In other words, the head is always on. After every read, it's always on a byte boundary. If you see what I'm saying. So if I tell it now, I have a controller which tells it which keeps track of where the head is, and tells the head how much more it has to go to get to the desired address space, the address location. And the units will be and it'll always move in movements of 8 bits. So the controller might tell it, go ahead 100 bytes. And then it'll go ahead 100 bytes. The controller will keep track of where it left off.
So this type of memory is like the regular memory, like not the program memory, like the data.
This is like the 1 terabyte hard drive that you have on your computer.
And that has to go in order.
And that has to go in order. I mean, you can jump around. It's like a record player, but it takes more time to go to certain locations than others. By the way, if I'm interested in doing a backup, let's say I want to back up my disk. I'm afraid that, there'll be a fire in my house and I have some critical photographs. So I want to do a backup of my disk. So actually it comes out that sequential a cassette recorder, a cassette drive, could actually be faster than writing it to a disk.
Why?
Because when you're doing a backup, essentially all you want to do is write byte after byte after byte in going forward. There's never a need to move the head. In other words, there's never a need to jump around. So I'll never move the head. I'll just scroll through if you think about it, the medium is scrolling, and the head on a tape recorder never moves. On a disk, if I wanted to copy a disk to a disk, the data on one disk to another disk, I would have, even if I'm going sequentially, from place 0 to place, 4 billion, I still will have to move the head because there's different lanes on the disk. And there's different platters also, the elevations. So there'll be a lot more movement of that. There'll be movement of the head, which is a much more complicated movement as opposed to just on a tape drive where I just move the medium. I just spin the wheels, and they just keep spinning. I just run them at a certain speed, and they go. So actually, backups are done typically not with a disk, but with a tape drive. Because in that case, I happen to know that I want to do everything in order. I'm never going to want to jump around. You understand? Because I'm just copying everything. When you're copying everything, you do it in order. Why would you jump around? Well, you want to copy just one particular byte, so then you have to jump around. So again, everything has its advantages and disadvantages. All right, now we have to talk about another topic. All right, somebody has to turn their microphone off, or I can do it if you want me to.
Do we still use tapes today?
Well, I don't know for sure, but I think we do. I mean, last time I was involved with backing up a disk, it was with a tape drive. That wasn't so long ago. In other words, it was already after the period of nobody using a tape drive for anything. And yet, we still use them for backups. I assume so. I assume that you can look that up afterwards if they're tape drive, how fast are the fastest tape drives. But again, they're only going to be used for backups. And you understand why. That's the place where they have a critical advantage or a comparative advantage. Okay. So now I have to talk about another concept called an associative access. And first I want to give you an introduction to it by talking about an associative array. You guys have never heard of an associative array, but there is such a thing in languages like PHP and maybe Python and other languages, Perl. Associative array is an array where I can store 2 values instead of 1. Think about it like that. I can store 2 values instead of 1. In other words, a normal array has an index and then a value. Like at index 7, I have the value refrigerator. And at index 8, I have the value elephant. And at value 30, right? I'm sorry.
I think we talked about these as, we'd mentioned them in a different class as maps. I think there are a lot of names for.
Yeah, you could call it a map.
Arrays.
You could call it a map, a mapping
So
function.
that, yeah.
A lot of times we talk about writing a function that does this, like a mapping function. You could call it a map. Yes, you could call it a map. But I think actually the most technical name is an associative array. Where, so let me give you an example of an associative array. For example, I could have an array called animals, where the index of the array is actually the value that I'm interested in. For example, the kind of animal I'm talking about. I've got a zoo, and I've got an array of animals. So I've got elephant is my first index. And then my second index will be chimpanzee, and my third index will be orangutan, and then my fourth index will be squirrel. And those are my indexes. So you guys, well, so what's the value for it? Where do you put the value? So now I can put another piece of information there. Since those are my indexes, I can say, for example, when feeding time is for the animal. I can put, 3 o'clock for elephants, 4 o'clock for chimpanzees, 5 o'clock for orangutans. So I can put the I can put a useful value, or I can even put like a list. I could put a whole, structure there with the names of all the elephants. Elephant, and then I could have like, Dolly, Teddy, and Frederick. Those are the names of my elephants. Those will be the value at location elephant. So it's very useful. It's good to call it a mapping, but it's very useful because I have essentially I'm storing two values. Now the question is, how are you going to get, the real problem with this is how are you going to find, why is this an array? How are you going to find value orangutan? Are you going to have to go through all the indexes until you can do it one by one until you hit on orangutan, and then you'll know where he is in the array? Or is there some kind of faster way to do that? I mean, if you have to go through one by one, then you didn't really gain anything. It's not really an array. The whole point of an array is that I can just throw in the index and boom, I'm at the location. I want to be able to just type in elephant and be at that location. I don't have to search through everything, and then I didn't gain anything. So,
but doesn't it find it by searching?
That's what I want to do. I want to do a search that takes me 0 time, though. I don't want to do a real search. I don't want to do a search that means I have to check every single one. Let's say I've got 10 million animals, and it happens to be the one I asked for is the end of the list. So I'm going to have to check every single string, if it happens to be equal to, whatever it is, Chihuahua. I don't know.
How does this type of memory solve that problem?
So that's what we're going to learn.
All right, and this, again, just trying to figure out compared to the regular computer, this type of memory is what in a regular computer? This is like
now we're talking about theoretical things now.
Oh,
we're talking about a theoretical concept, not memory. It's just there's such a thing as associative access. This is a type of random access. It's a type of, we talked about a sequential access and random access. Now we're going to talk about a particular type of, you want an example of something that works this way? I don't know. But there is associative access. I should really draw you a picture of it.
And for the random access, we're going to be able to learn how to find something with random access.
I'm going to show you. I'm going to show you right now how to do it. Wait, how do I have a whiteboard? Where's the whiteboard?
On Zoom, there's on the share button, there's an option for a whiteboard.
New share. Okay, whiteboard. Okay. Now you won't see my slides, just see my whiteboard. So here I'll show you how you construct associative. First thing you do is you make a box. Can I get rid of this? Will I still have a writer? Oh, now what? Oh, now I lost my tablet. Now let's do stop share. Let's do new share again. Let me try that again. Okay, so I have my box. We're going to call this box the ALU. Yeah, I'll just show you one basic idea so you have some idea of what we're talking about. I can move this. How do I get rid of this? I got this menu in the middle of my page. Here, move it over there. Okay, that's the ALU. And let's say I have over here this box is done. This is a register. And I have here the address. A D R E. No. Well, okay, that's enough. Address. That's the address. And I have over here a piece of memory. and a content. I have here, this is the address. Every memory has its address. So here's like the address of it. AD, oh, I really need a mouse. ADD, and here is the content. For example, you know, 12 o'clock, feeding time. I don't know, 12 o'clock. And I have another one over here, which is another address and another, you know, every memory has its address and its value. Address and value here. So this one is, let's say, chimp. I gotta do this fast. Chimp, and he's, let's say, at 14 o'clock. Military time. Okay, so, and I have another ALU here, and another ALU here, and I take this address and I shove it into this ALU, and this address into this ALU, and this address also keeps going into this one and keeps going into this one. So this address is going into every single ALU, and this address here is going into here, and this address here is going into here. And the ALU performs a subtraction, and it's got a 0 line here, as we learned. 0, whatever, that's the Z supposed to be. That's the 0. Now, if I put in here elephant, and I put in here elephant, here is elephant, orangutan, and chimpanzee. So if elephant is here, and I put in, let's say, I put an elephant here, then the elephant of here is going to go, and the elephant here is going to go, and we're going to do subtraction. We're going to get 0, and on this 0 line, I'll get a 1. On every other 0 line, I'll get a 0, because this is orangutan. It's not when I subtract elephant from orangutan, I don't get 0. So therefore, I know what?
This is associative.
Is associative. This is also what's called a parallel search, because I'm searching in parallel. I don't have to check this one and then check this one and then check this one. The electricity goes on all these lines, and this is it, and I just turn the switch, and boom, everything goes into the ALU, and I get 1 0 0 0 0 0 0 0, and I know it's on this first one. And therefore, I can search in hardware for the data that I want based on an address which is not numerical, or is not, in other words, is not. I'm not checking 0 1. Now, is this the way we did it before? You know, if this was 17, we basically did the same thing, but we found 17 with a multiplex or something. Here I have to use an ALU. It's more expensive. ALU is expensive. More logic gates here. Of course, the specialized ALU, which is just doing subtraction. But that's the idea of, and let me just go back to the slide for a second, and then we'll end there. What is this? Yeah, new share. Okay, so this is a type of random access. We access by value instead of by address. We perform a parallel search. So when you're programmers, you think a parallel search means a loop, but that would be an iterative search. A parallel search really can only be done in hardware, as far as I think of it. Parallel search is done in hardware. The address of the value sought will be output to a special register. So again, in my example, I did like an actual content, but you could theoretically have the elephant be the value, and it just tells me where it is in the array. And the other thing be in as I had a double content array. You could have a content versus address. We will discuss this further when we discuss cache memory. Fine. But that's the basic idea. Okay, we'll stop here. Good luck, guys.